Alright, welcome everyone to this next video here on acids and bases. In this video, we're specifically going to be talking about weak bases. So, weak bases behave in similar types of ways as weak acids, okay? But except we're dealing with a base instead of an acid, right? We'll talk about the equilibrium constant for a weak base Equilibria, given by this notation K sub B, B right for base, right, acid for Ka, right? And for the Kb reaction, we have to include water. So for example, a typical reaction, right, this weak base equilibrium reaction is going to be this, okay? Right? Where A minus here is our weak base, right? And it reacts with water, which acts as the acid, to form weak acid and conjugate base, OH minus, right? So a specific example of this are things like amines. So ammonia, we often talk about in this class, NH3, okay? But even methylamine and such, okay? But right, ammonia reacts with water to form ammonium and OH minus. Okay. Other examples of weak bases are conjugate bases of a weak acid, right? All of the weak acids we just talked about, they're conjugate bases or weak bases, right? So HClO, the weak acid, has a conjugate base, ClO minus, which is a weak base, right? Acetic acid, okay? So acetic acid, right? We often write it as this, but it could also be written as C2H3O2H. Okay. Now, often I won't use this notation. I'll mainly use this, right? And so acetate also is often written as CH3COO minus, right? But these are examples of weak bases, which are conjugate bases of your weak acids. Okay, and again, it basically, right, our only strong bases are like alkali and alkali earth hydroxides, right? Potassium, OH, calcium, OH. Right? These are strong bases. Okay, everything else is going to be a weak base. Okay, and again, these weak bases undergo a acid-base reaction with water, right, to form the conjugate acid and OH minus ions, right, right, and so you have these things in aqueous solution, right, and so the Kb, that base equilibrium constant, is going to be this BH times OH minus divided by B. Okay, right, and this is kind of a general form, right, for these equilibrium constants, right? But again, if you don't even memorize any general form, just remember, right, when we talk about equilibria, that the equilibrium constant is just product over reactants, right? And this is our equilibrium reaction, okay? And so we just derive that equilibrium constant from that. Okay. Now, one final thing to note about weak bases, especially those that are conjugate bases of an acid, right, is that the product of the Ka and Kb for a conjugate acid-base pair is equal to Kw. Okay. And so often we'll only be given like Ka or Kb, and we have to use this relationship between them to get Kw, right? Because, for example, if I have a weak acid HA, right, H plus A minus, and then I have, right, A minus itself is a weak base and undergoes this reaction, right, with water to form H3O plus, sorry, not H3O plus, I don't know what I'm doing here, right? A minus is a base, not an acid, right? This forms HA plus OH minus, right? So the Ka here is concentration of A minus, concentration of H plus, over concentration of HA, right? And Kb is equal to concentration of OH minus times concentration of HA over concentration of A minus, right? So if you notice, if you multiply Ka and Kb together, things will cancel. The product of Ka, Kb will just come out to be H plus times OH minus, which equals Kw, right? Equilibrium constant for the ionization reaction in water. Okay? And so you kind of just see where this relationship between Ka and Kb come, right? And again, this relationship should make sense, right? Because the larger the value of Ka, the stronger the acid. But its conjugate base is weaker, right? Which means the conjugate base's equilibrium constant has to be smaller, right? So the larger Ka, the smaller Kb, right? Which goes in line with our statements. The stronger the acid, the weaker the conjugate base, right? The stronger the base, the weaker the conjugate acid, okay? All these things are kind of tying in together.